Okay, hello everyone. The first chapter of storage management is memory management. Later on, we will see virtual memory and file systems too. But this chapter objectives include providing a detailed description of various ways of organizing memory hardware and exploring various techniques for allocating memory to processes. Lastly, we want to discuss in detail how partitioning, paging, and segmentation work in computer systems. So first, let me give you some background information on memory management before starting our discussion on this topic. So remember that programs need to be brought from disk. Okay, need to be brought from disk into memory to be executed. This involves placing them within a process, and main memory and registers are the only storage areas directly accessible by the CPU. Uh, Access times can differ for accessing main memory and accessing register. Register access is fast, taking just one CPU clock cycle or even less. Main memory access, on the other hand, can take multiple cycles, which make it slower in comparison to register access. To bridge this gap, a cache is positioned between main memory and CPU registers, and ensuring the correct operation requires memory protection mechanisms. Yeah, so overall, managing memory involves the collaboration of both the operating system and hardware to accommodate multiple processes in main memory. So now let's start talking about how to allocate memory to processes. But you should know that before a user program can run, it undergoes several steps. Now let's look at these steps in as shown in this figure. So source files are created by the developers, by you. Each source file includes high-level source code. First, high-level source code is transformed into machine code by compiler so that the computer can understand this source code. As I said, this operation is done by compiler. Then the machine code is assembled into project code, into object code, object code by assembler. So we obtain object modules out of these source files. In order to create an executable program, the assembling part is essential because linker will use these object modules in order to create an executable file. So the next step is linking, which links different object codes and libraries to produce a wrapped up executable binary file. And placing the software into memory and preparing it for the execution is known as loading this operation, and it is done by loader. Okay. So finally, the user program is executed and the CPU carries out the instruction stored in memory. Actually, this multi-step approach demonstrates the procedure a user application must go through in order to function properly. Every phase is essential to successfully preparing and carrying out the program. Now let's walk through an example of C compilation. So the process begins with header files such as definitions, make age, okay? And these header files contain declarations and macros used throughout the program. We also have many source code files like main.c, help.c, and other.c. The C preprocessor uses the source codes handling directives, macros, and other preprocessor commands. It produces an expanded version of the source code. Okay, so then the compiler translate the pre-proposed source code into assembly code or an intermediate form. For each source file, the C compiler generates corresponding objects as main.o, help.o, other.o. These files contain machine code that is specific to the architecture, but they are not still linked to a complete program. At the last step, the linker combines the object files with external libraries. Okay, external libraries such as library C.A to create a complete executable program. The result is an executable binary program, typically named a.out, unless you specified otherwise. Now, you may wonder that what creating object modules and linking operations are. Let's look at the object modules in system memory from closer. Initially, each object module operates within its own address space. This means that addresses used within a module are specific to that module and they are not globally applicable. All addresses within an object module are relative to the beginning of that module. In other words, the addresses are expressed in terms of their offset from the starting point of the module. To better understand these two properties of object modules, I want to illustrate this with two example object modules, module A and module B. The module A has its address space ranging from 0 to 400. 0 to 400. Instructions within module A, such as call B, move P to X, and branch to 200, are executed using addresses relative to the start of the module A. Okay. So module B, on the other hand, has its own address space from 0 to 500. Instructions within module B, like call A, move R to X, and branch to 200, use addresses relative to the beginning of the module B. This relative addressing approach allows each module to work independently within its designated address range, and it avoids conflicts and provide a modular structure for the program. So now we can continue with what linker does by using object modules. Okay, actually the linker utilizes tables present in object modules to connect, or we can say link, multiple modules into a single linear addressable space. The result, often referred to as load module, provides a single continuous address space. This means that the addresses within this space are now linear. The new addresses assigned during the linking process are still relative to the beginning of the load module. Even though the modules were initially operating in their own address spaces, the linker resolves the relative addresses to create a unified address space for the entire program. So in this example, you can see a unified address space for the entire program. So these two object modules are being linked into a load module. The load module, as you can see, it's the combination of object modules A and B. You can also notice that load module provides a linear address space from 0 to 900. This linking process ensures that the program is unified and can be executed successfully as a single entity with address relative to the beginning of the load module.